Our next video is going to be about the first law of thermodynamics. The first law of thermodynamics looks like this. Delta U is equal to Q plus W. Delta U means the change in internal energy of the gas. And it's extremely important to remember the relationship between temperature and internal energy. We had previously stated that U is equal to 3/2 nRT. That allows us to calculate how much internal energy there is for a gas at any given temperature. If the temperature doubles, then the internal energy would double as well. So any change in internal energy would equal to 3/2 nR delta T. So any change in temperature, the temperature increases, the internal energy of the gas increases as well. If the change in temperature decreases, then the internal energy would decrease. Now, as for the other parts, delta U equals Q plus W. Q means heat. Positive Q simply means that heat was added to the system, which would, of course, raise its temperature, perhaps, while negative Q means that heat was removed from the gas. Okay? Now, work itself is a more interesting idea. And if you think about what work really means in our original mechanics terms, it was talking about a force applied over a certain distance. So what does that really mean when we're talking about gases or liquids? How does work have anything to do with changing the internal energy of a gas? Well, if you look at something as simple as this idea here, let me switch to a different model. Okay. So in this example over here, we simply have water being stirred constantly. It's stirring, 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 stirring. There's a force being applied over certain distances. You can see the block dropping. Now, what's interesting to note, of course, is this blue line over here. That's the temperature of the liquid. As the block is dropping, it's actually increasing the temperature or the internal energy of the liquid itself. So if you had a cup of ice or a cup of ice water, if you were to stir the cup, the ice would melt faster simply because your kinetic energy will be turned into thermal energy as well. So when we talk about work, we really are talking about applying a force over a distance. Okay. Now, but what force over what distance are we talking about when we talk about work? So over here in this example, we have gas molecules that are freely floating around. And when I talk about work being done on this system over here, that's simply talking about the force applied by the piston over a specific distance. And notice that as we're compressing it, we're adding energy into the gas. And the gas molecules are actually moving faster than before, which is why the temperature increased as well. So overall, when we talk about positive work, we're literally talking about an outside force compressing the gas. So if I were to write down my definition over here, positive work is an outside force compresses the gas. So the volume is decreasing, but the positive work is they have the outside force. Now, negative work, on the other hand, negative work will be about the gas itself using its energy to push back out. So the gas uses its own energy to push the piston back out. In this case, volume increases. So just to recap that, positive work means that the volume is going to be decreasing because you're compressing the gas. But once you let go of that piston, once the outside force lets go, the gas is going to push right back out. So negative work means that the volume is going to be increasing. Okay, so keep that in mind because that's going to be very important when we start doing our pressure volume gas law graphs. Now let's do a quick example of delta U equals Q plus W. An amount of heat of 2,500 joules is added to the system, so that's Q, and 1,800 joules of work is done on the system, so therefore it compresses the system. So it's going to be a positive work. So when they ask us what's the change in internal energy, the formula would be delta U equals to Q plus W. So that equals to 2,500 joules plus 1,800 joules, which equals to, of course, 4,300 joules. So the internal energy of the gas increased by that amount. But let's add a second part to this. Let's say that this gas, this system, there were 3 moles of gas. The question is, how much did the temperature change by when we added in all that energy? So in this case, we know that delta U is equal to 4,300 joules. But also remember that delta U has a second formula, that delta U is directly related to temperature. So we can also set it equal to 3/2 nR delta T. Okay? So in this case over here, notice, does the type of gas matter? No. The type of gas has no part in playing with how much internal energy there is. It's just that if you have a smaller gas particle, it's moving faster. A larger gas molecule would be moving slower, but the internal energy would be exactly the same amount. So if we were to work this out, we know, of course, that we're looking for delta T. So delta T would equal to 2 times delta U over 3 nR, which would equal to 114.99 Kelvin. Okay, so keep in mind that there's 2 formulas for delta U. For part B, they ask, what would the internal energy be if the 2,500 joules was added while 1,800 joules of work was done by the system? So if 1,800 joules of work was done by the system, that means the gas is using its own energy to push back out. So for part B, delta U equals to Q plus W, end up with 4,300 joules you end up with 2,500 joules minus 1,800 joules, which is equal to 700 joules. Okay, so let's clear off the work here. Okay, so now if we take a look at an actual piston again, we can talk about how work is being done whenever the piston, of course, is applying a force onto the gas itself. So in this case, the gas, of course, would be the molecules inside. And work is equal to the force times the distance that it was compressed. However, there's an alternate formula for work. based on the original formula and based on what we've learned so far. We know that pressure is equal to F over A, the force, of course, being this force over here, and over the cross-sectional area of the piston itself is the area. So force, we could say the same thing as the pressure times the area. So if we were to turn this into the pressure times the area times the distance that's being moved, okay? Well, if we take the area times this distance over here, ultimately what we end up with is volume, or really the change in volume based on the distance that it moved. So an alternate formula for work, if we just scroll over to this box over here, is that work can also equal to negative P delta V. Okay? But what is that negative sign there for? Well, really, it's a reminder and really to help you calculate that when you have a negative delta V, meaning that the volume is being compressed, and if you take that negative from the front times the negative, you end up with positive work, because you always have positive work whenever the gas is being compressed. If you have the volume increasing, in other words, a positive delta V, in other words, the gas is expanding, when you take that negative value from before and put it in front, you end up with a negative work. Okay? So negative P delta V, it's not a formula that's used very often, but it's important to understand where it comes from. So this formula assumes a constant pressure. And if it's not a constant pressure, you can't use the formula. But let's just try using this formula one time, if it did work out. This is on a page later, where a gas is enclosed in a container with a piston of cross-sectional area of 0.15 meters squared. So we know the cross-sectional area. The pressure is maintained at a constant, which maintained means it's constant, 6,000 pascals. So the area is 0.15 meters squared. The pressure is 6,000 pascals, which is the same thing as newtons per meter squared. And the piston moves inward by 20 centimeters. So if you can imagine this, we have a piston moving downward 20 centimeters. Okay? And if we know that the distance it's moving down is 20 centimeters, or in other words, 0.2 meters, we can calculate what's the change in volume. Because the change in volume is simply equal to the area times the distance that it moved. So 0.15 times 0.2 is equal to 0.03 meters cubed. So if we're looking for the work that was done by the gas, work is equal to negative P delta V. So in this case, by the way, it's a negative delta V because it was compressed inward. So we end up with negative times 6,000 pascals times negative 0.03 meters cubed, and you end up with the work equaling to 180 joules. Okay. Now, for the second part of the question, they're assuming if the internal energy, that's delta U, decreases by 8 joules, if delta U is equal to negative 8 joules, they're asking us how much heat was removed from the system. What's Q? So if we do delta U equals to Q plus W, Q is simply equal to the negative 8 joules minus the 150 joules that was taken away. You end up with negative 158 joules. Okay, So this is just a standard question involving delta U equals Q plus W, as well as work equals to P delta V. Now, the thing is, though, the formula P delta V is much more commonly used when we're talking about graphs. Now, the reason it's important when we're talking about graphs is, well, on the y-axis we have pressure, on the x-axis we have volume, and whenever we look at a graph, we either look at the slope or the area. In this case, area is going to be much more important because the area deals with the y-axis times the x-axis. So in other words, the area is equal to work. So this area over here is equal to work. But you have to be able to look at the graph and say to yourself, is that positive work or is that negative work? Well, the fact is, if you look at the arrow, the volume is increasing. If the volume is increasing, that means that this is going to be negative work. Okay? So anytime we look at a graph and we're looking at the area underneath it, the area underneath is equal to work, and you should be able to tell if it's positive or negative. Okay. So even if you take a look at these examples over here, in fact, let's zoom in on them a little bit more. Okay. So taking a look at this first example over here on the left-hand side, we have two steps to this gas process. We have a gas that's decreasing in pressure while the volume stays the same, and then the pressure stays the same while the volume is increasing. Okay, those are very specific names, and we'll get to them later. But right now, if you take a look at this first line over here, how much work is technically done during that first process? Well, if you look at that line, how much area is there underneath the line? Of course, the answer is 0. So the answer to this part over here, this would equal to 0 work. Or really, sorry, work equal to 0 joules. The second part of the line, however, we have an increase in volume. Now we have an area underneath our graph line. So this area underneath is equal to a negative work. Okay? And if you take a look at the second example on the right-hand side, during that first process, we have a negative work being done. And that's equal to the entire area underneath. So during the second line of that process, we have the volume staying constant. And when the volume stays constant, there's no work being done because the gas isn't being compressed or expanded. So there's 0 work. If you look at this last example over here, now in this case the line is curved, but I'm just going to assume the line is straight for now. Okay? When the line is straight, it's still easy to solve for the work done because you're solving for the area underneath. It's just that you have to break it down into a triangle and a rectangle. Okay? And you add the two areas together to solve for the total negative work. But if there had been a graph instead that was with a curved line, now I'm going to draw it like this. Is it easy to solve for the area underneath that shape? No. And they don't expect you to either. Rather, you're going to have to use a formula to solve for what the work is in that example. And we'll do something like that later. But what I do want to point out is notice that the volume is decreasing. So in this example over here that I just drew, this would be considered a positive work as it goes from the beginning to the end. Okay. So here is another example. Answer in terms of PO and VO, solve for the work done by the gas and the temperature change of the gas itself. So this one's a little bit more complicated, but ultimately we can see that the gas process begins here and ends there, which means if we're looking for the total work, we have to solve for the total area underneath that graph line. So it's simply talking about breaking that into a triangle and a rectangle. So during this first portion over here, I can see that the width is 1 VO, the height is 1 PO, so therefore the work during that square is equal to, and because the volume is increasing, so it's going to be negative PO times VO. The work during this part where it's half, the work is going to equal to negative 1/2 PO VO because it's a triangle. So the total work being done in this area would equal to, work is equal to negative 1.5 PO VO, because you have 1 PO VO combined with a half PO VO to solve for the total work in a variable only question. The next part they ask us is, what's the temperature change? Now this deals with the combined gas law. So whenever given the combined gas law, we're talking about PV over T, or P1 V1 over T1, equals to T2 V2 over T2. The most important thing to remember about this formula is that this is equal to a constant, meaning that the total value can't change. Any multiplier you put in has to be canceled out. So when you go from, initially it's PO, VO, and TO, when you go to the second point, now the pressure has doubled. The volume has doubled. What number has to go in front of temperature so it cancels out all the multipliers? So of course, to cancel out the double pressure, the double volume, you have to have 4 times as much temperature, so that way it all cancels out. So the answer in this case would be T2 is equal to 4 times the initial temperature. Now let's take a look at the example over here. Number 10. This one's a very straightforward question. A gas expands from I to F along the 3 paths indicated below. Calculate the work done by the gas along each of those paths. So it's really 3 separate problems in one. The first problem deals with IAF. So if I were to redraw that, IAF goes from here to here to there. So if I'm looking for the work done, I need to solve for the total area underneath the line. So that means even though this second line, of course, doesn't go all the way down, underneath that first line, it goes, I solve for the total area underneath. The second line doesn't even matter because there's no area underneath that line, there's no work. But that first part, I just solve for the total area. So if I go to this graph over here, I'm looking for this area. I can see that the total pressure is equal to 4 atm, which is equal to 4 times 10 to the 5th pascals. The total volume here is equal to 2 liters. The change in volume is equal to 2 liters. Now the conversion factors from liters to meters cubed is that you just multiply by 10 to the negative 3rd. So this is really 2 times 10 to the negative 3rd meters cubed. So if I'm looking for how much work was done, work is equal to negative P delta V. I'm allowed to use the formula in this case because I do have a constant pressure for that first line. Or I could simply solve for the area of the rectangle. 4 times 2 is 8. So in this case, you end up with negative 8 times 10 to the squared power, and that's joules, or in other words, negative 800 joules. And that's the work for IAF. If I want to solve for the work for IF instead, well, now I'm looking at a line that looks more like this. So I want to solve for the area underneath that line, so that would end up equaling to a triangle. So I have the triangle over here, plus the rectangle underneath. So the triangle for the first part would be, let's see, you have a total height of 3 times 10 to the 5th pascals times a base of 2 times 10 to the negative 3rd meters cubed times 1/2, of course, and this would equal to negative 300 joules. So this is for the triangle. For the rectangle underneath, that's simply going to be a total pressure. So for this rectangle, it's a total pressure of 1 times 10 to the 5th pascals times a base of 2 times 10 to the negative 3rd meters cubed. So this would equal to negative 200 joules. So the total work for that IF would equal to negative 500 joules. The next lesson is going to be about special situations that occur on the PV graph, and that will be the next video.